So this video goes alongside the test that I've emailed you back, so I have that in front of you as I go through each question to justify the answers. So the first question, 1A, is about the mechanism for step 1. So this is step 1. You don't need the actual mechanism written out, but the answer is that alkenes making halogen-alkanes is electrophilic addition. So HBr here is acting as the electrophile. The double bond on the carbons attracted to the hydrogen, which is slightly positive in the HBr, bromine being more electronegative. So HBr is the electrophile and it's being added to the alkene, making 2-bromobutane. Compound J is an intermediate in between 2-bromobutane and butanone. So going from a halogen alkane to a ketone. So it's going to be an alcohol. And to make butanone, you've got to go from a secondary alcohol, butan-2-ol. And to make that from 2-bromobutane, you need sodium hydroxide aqueous to do a nucleophilic substitution, making butan-2-ol. Part C is the year 13 new stuff. So this is the nucleophilic addition mechanism for CN- with carbonyls. So for the reagents, it's KCN and acid, or HCN will do. You can't just put CN-, that's not a reagent, that's an ion. And for the mechanism, 1 mark is for a curly arrow from a lone pair on the CN- attacking the delta positive carbon of the carbonyl group. 2nd mark, the carbonyl bond opening up, leaving the pair of electrons on the oxygen, giving a negative charge. 3rd mark is for the intermediate with a negative charge on the oxygen, and the 4th mark is the curly arrow from the lone pair of electrons to the H+, not an arrow showing the H+ moving. And so why does this reaction produce a racemic mixture? Well, butanone is a ketone, which is a planar molecule, it's trigonal planar, 120 degree bond angles. So the nucleophile, the CN-, can attack from either side of the molecule. Likelihood is 50-50, which means if it comes from the left, it'll produce one enantiomer, comes from the right, it'll produce the other. So you get a 50-50 mix of both enantiomers from this reaction, which is a racemic mixture. So question 2 gives you the wave number of 3230 to 3550. So on the back of the periodic table, in table A, that shows that it's an OH bond from an alcohol. You need both of those for the mark. And the evidence tells you it's C4H10O and that they're all straight chain alcohols. So 4 carbons in a row. Only 2 isomers you can get are butan-2-ol and butan-1-ol. A must be the butan-2-ol because it forms a ketone which can't be oxidized, and B forms butan-1-ol, which is an aldehyde which can be oxidized. And that's the evidence in table in part B. So part C tells you that the alcohol C cannot be oxidized, which means it must be a tertiary alcohol, shown here on the right hand side. And the bond that it gives you, 1620-1680, again on table A, that's a carbon to carbon double bond. So here we're making an alkene from this tertiary alcohol. And this reaction is elimination. Okay, so concentrated sulfuric acid is the reagents that you need, and we reflux it, or high temperatures. And the H+ from the acid protonates the OH group, making H2O+. That falls off of as water with a hydrogen from one of the neighbouring carbons, doesn't matter which one, which leaves you with the alkene plus H2O. So this is the kind of the 5th mechanism from alcohols that we need to know. So part D concentrates on D, which is a branched alcohol, which says during oxidation you can distill off S, and to reflux you go to T. So from an alcohol being oxidized, to distill it off you get the aldehyde. Full reflux, it goes all the way to the carboxylic acid. And in terms of intermolecular forces, the aldehyde has only got London dispersion forces and dipole-dipole forces between the molecules, whereas the carboxylic acid T has hydrogen bonds from the OH group between 2 molecules. So the carboxylic acid with hydrogen bonds is a stronger intermolecular force, therefore requires more energy. So when you heat this up, S, having the low boiling point, will boil first and can be distilled off. And for D part 2, we want to use the infrared spectra as evidence that no oxidation has taken place. And the first is that the OH peak at about 3350, the broad peak, is still there, saying you've still got an alcohol. And had it been oxidized, you would have had a carbonyl peak at 1750, which isn't there. And had it gone all the way to a carboxylic acid, not only would you have the carbonyl peak, you'd also have the OH peak from the carboxylic acid. But that's lower down, that's about 2500 to 3000, which would bump into the very sharp CH bond. So no oxidation has taken place here, you just need 2 out of 3 of those. So for question 3, here we've got esters being made either by an alcohol and acid anhydride or an alcohol and deacyl chloride. Here we have the acid anhydride. And the reaction here is that the alcohol's OH group will attack either of the carbonyl carbons. Carbonyl carbons will then open, close and release CH3COO, which will go with the hydrogen from the alcohol, leaving your ester. The equations at the bottom. At the top I've put the displayed formulas just to be able to show kind of how this rearranges, and there's no problem drawing out the displayed formula when you're asked for a chemical equation. The IUPAC name of the ester, well, I've drawn it out here. So you've got the ethanoate group, CH3COO, and the alkyl group on the right hand side, you've got a branched alkyl group. So there's 2 carbons as a stem, which is the ethyl group, and then you've got a methyl branch. So this is called methyl-ethyl ethanoate, where the methyl-ethyl group on the right is the alkyl group. It's branched. We haven't seen this much, but that's how we would name it. The mechanism for the nucleophilic addition and elimination, which we've been studying this term with acyl chlorides, this is standard for AQA, so this is one definitely to learn. First mark is the curly arrow from the lone pair on the OH group on the alcohol to the delta positive carbon of the carbonyl. Second mark, the carbon-oxygen double bond opening up. Third mark is for the intermediate species on the right, which has a negative charge on the top oxygen with the lone pair and a positive charge on the middle oxygen that's used its lone pair to bond with the carbon. The fourth mark is for the rearrangement of the electrons in the final step. This is the elimination part, where the lone pair on the oxygen with a negative charge reforms a double bond. That's what I'd like to do, have a carbon-oxygen double bond, and chlorine can fall off as a chloride ion. So that's the other arrow. And finally, we regenerate the hydrogen, which is going to go off to make HCl by breaking the OH bond, and the electrons have to go back to the oxygen to neutralise that positive charge. So all those 3 arrows on the right hand side give you the final mark. And then we've got the question about our vegetable oils. So here we've got our triester, and the first reaction with sodium hydroxide to form soap. And here the sodium hydroxide gives OH minus ions, which are going to break the carbon-oxygen ester bond to regenerate glycerol. And then you've got the fatty acids being carboxylate ions bonded with sodium. So we've got that hydrophilic head with Na plus and O minus dissolves in water, and the hydrophobic tail with 17 carbons. Here you need 3 sodium hydroxides to balance. And remembering that biodiesel are methyl esters, well, out of these long carbon chains, having a methyl group on the alkyl side will give us biodiesels, and the one with the highest MR is going to be the one with the most atoms. So all of them got 17 carbons. The middle one, H33, will have the highest mass. So we're looking for C17, H33, COO, and then a methyl group on the other side. So question 4 asks for the skeletal formula for propane 1,2-diol. So first of all, skeletal formulae. Here we have the skeletal formula for propane, 3 carbons, second one has the kink in the middle, and adding 2 OH groups to this will give us propane 1,2-diol. Not important which is the first carbon. I've put it on the end here for the reaction. So whether that last OH is on the 3rd carbon or the first as we see it, both of them are going to be propane 1,2-diol. And we're asked for the full oxidation product for this reaction. And so I've written out this displayed formulas so we can see we've got a secondary alcohol and a primary alcohol. When we fully oxidize this, we're going to get a carbonyl or a ketone in the middle carbon, and the primary alcohol will oxidize all the way to a carboxylic acid, which gives us this molecule at the top right as the final product. So in terms of the symbol equation, CH3CH brackets OH, CH2OH is propane 1,2-diol, and we're making CH3CO, COOH. And from this, we've got 8 hydrogens on the left, only 4 on the right, so we're going to make 2 waters, and for this we'll have 5 oxygens on the right, 2 on the left, so we need 3 of these oxygens in brackets. And with potassium dichromate, we don't use potassium dichromate to balance it, we just use the O in bracket and each of those is one oxygen atom. In part C, we're asked for the apparatus for a reflux. A-level students are awful at drawing reflux and distillation apparatus, so practice this. All you need is a round bottom flask at the bottom with a condenser vertically upwards from that, making sure there's no gaps between the round bottom flask and the condenser. Condenser is open at the top and you've got the jacket on the outside. So a really simple diagram is what they're looking for, not 3D, not a work of art, something very scientific. So this would be your reflux apparatus. Your second mark is to label the diagram. That's what it's asked for. So round bottom flask at the bottom, condenser at the top is all you need for the second mark. If you want to show off, you can label the water in and out and heat at the bottom, though you're not asked to do that here. Many cases you are. For part D, it asks why we use anti-pumping granules. This is to allow smooth boiling or to create small bubbles. If they weren't there, bubbles struggle to form on the glassware. And so the whole thing superheats, it goes above its boiling point and then just bumps, and that just means the whole thing kind of splashes upwards towards reflux condenser. We don't want that. So anti-bumping granules allow smooth boiling, avoids large bubbles forming, creates smaller bubbles during reflux. And lastly, we're asked for products that would have formed during partial oxidation. So here, remember, we've got primary alcohol and secondary alcohol. Well, the first thing is if the primary alcohol only oxidizes to an aldehyde, not a carboxylic acid, that would be your first partial oxidation product. Or if that primary alcohol oxidized all the way to a carboxylic acid, but the middle carbon, the secondary alcohol, hadn't oxidized yet, that would be another partial oxidation product. Or you could have the middle carbon oxidizing fully to a carbonyl, making the ketone, where the primary alcohol hasn't yet oxidized. That's another partial oxidation product. Or finally, you could have the middle carbon fully oxidizing to the carbonyl, but the primary alcohol only oxidizing to an aldehyde. So any of these four would be the structure of a partially oxidized product.